Hey everybody, in this video we have two goals. The first goal is to learn how to find dot products, which is this, and the second goal, which stems from the first goal, is to figure out why the bond angle in tetrahedral molecules is 109.5 degrees, and dot products will help us achieve the proof behind the bond angle that we are going to look at later. But for now, let's all review what vectors are, and if you already know what vectors are, check out the description in the YouTube video and skip over to the part where I talk about dot products, and that exact time I will put in the description. So first off, I'm going to review what a vector is, for those who haven't seen a vector in a long time. So a vector is simply a quantity having both a direction and a magnitude. And another word for magnitude is size. So pictorially, it looks like this. A vector, you can think of it as simply an arrow with a length to it, and that length is the magnitude. So this vector, we can see, has a start, and we will indicate that with a dot and an end. And that end will have an arrow on it, and at the tip of the arrow, there will be a point. And that will be the ending point, or the terminal point of the vector. Now, I labeled this vector with 2 points, so the initial point is x1, y1, the ending point is x2, y2. Now, as we can see in what I drew, a vector can be represented by a variable with a little hook on top of it, and that's just the proper notation for vectors. Now, okay, I kind of skipped too far, but here we are back again, and as you can see, a vector is written in between two pointed brackets, and within those pointed brackets, you're going to have something similar to a coordinate point, but the two components are not going to be locations. They're actually going to be changes in x and changes in y, at least in the xy plane, as shown here. So in this case, our change in x will be the first component, and the change in x is x2 minus x1, or the ending x minus the starting x. Now the change in y is basically the same thing, but in the y direction. So y2, which represents the ending, and y1, which represents the start. So now that we know how a vector looks like, let's actually try to find some vectors. So here we have an initial point and a final point, and I want you to find the vectors representing these two vectors. So in this case, r will simply be the change in x, which is 3 minus 0, 3, and the y component will be 2 minus 0, or 2. Now, same goes for the s. 4 minus 1 is 3, and 3 minus 1 is 2. And hey, what do you know? R and S, two vectors, are identical. But the only thing different about them is that they start at initial points. But otherwise, they're the same exact vector. And guess what? Vector doesn't care about where you start. It just cares about the change in x and the change in y. So let's graph this to see how it looks like. So 0, 0, and 3, 2 will represent our first vector, which we will call vector r. And the second vector is 1, 1, and I kind of misdrew it, but you can tell where I'm getting at. And here's 4, 3. And notice how these two vectors, well, let's just make this a little bit more specific and call this vector s. You notice that these two vectors go in the same direction, and they also have the same magnitude as well, as you can see here. The two magnitudes are the same and the direction is the same. So both of these are the same exact vectors. Now, guess what? Vectors can be in the 3D space as well. So this is a 3D coordinate system, and it kind of looks like the back of a cube if you think about it. The z is always the up and down. The y is always the horizontal, and in this case, the x will be pointing towards or away from us. So let's try to find the vector r given the initial point, 0, 0, 0, and note that this third component is going to be the z component, telling us how high or how low it is. And in this case, the terminal point of the vector will be 2, 2, 1. Now, how do we get that? Well, we can see that this is the x component, so 2, and we can see that the y component is 2 as well. So we can have traced that over, and we have to move it 1 up since the z component is 1. So we kind of just move it up a bit, and voila, that's the point right there. So it's kind of hard to see now, but I'll change it to a different color so you can see that a little bit better. But that's our vector, and we need to find the components for it. So in this case, we have to find delta x, delta y, and that third dimension, delta z, because we have an extra variable. So the change in x is 2 minus 0, 2, 2 minus 0, 2, and 1 minus 0, 1. So this vector is represented by that. Now let's talk about some rules involving vectors before we get into dot products. So a constant times a vector will essentially distribute it into both components, both the x component and the y component of the vector. And in the end, you get the vector c times u1 and c times u2. And u1 and u2 are just arbitrary variables representing, for example, this is the change in x and this is the change in y. And as you notice, it's kind of like the distributive property in math, where we go 2 times 3 plus 1, you just go 2 times 3 plus 2 times 1. Kind of like that, but it's in the world of vectors, so it looks a little bit different, of course. Now note that when you multiply by a positive constant, let's just add a note. So a positive constant, when you multiply by a positive constant, it will be in the same direction, but it'll have a different size. So in this example, we have a positive constant c being multiplied by the vector 1, 1. And as you notice, it gets distributed and you end up with the vector c, c. And if you think about it, the constant c is going to be greater than 1 because it is actually scaling up the vector as shown in the image. And if we have a c that is less than 1, then the vector will become smaller since you're multiplying by a fraction. So in this case, we are multiplying by constant c, and as you can see, the direction is the same. So same direction, but you notice that the size difference is enormous. And yeah, that's how vectors work when you multiply by a constant. Now let's figure out what happens when you multiply by a negative number. Now, multiplying by a negative will flip the direction. So you have a negative c, you're going to flip the direction and scale it up or down accordingly. But let's focus on negative 1 for simplicity. So a negative vector u, you can think of it as an invisible negative 1 times the vector u. And if you think about it that way, we're basically distributing negative 1, and you end up with this new vector, negative u1, negative u2. Now let's look at this image, and let me fix this image so that it's more representative. And as you can see, u1 and u2 are both positive for the vector u, as you can see, because we're moving up, which is a positive delta y, and we're moving to the right, a positive delta x. Now, if we take the negative of the vector, you notice that the direction flips and goes kind of like a 180-degree turn. And as you can see, what ends up happening is that our components are switched from being positive to negative. So we're moving down now, a negative delta y. And we're moving to the left now, a negative delta x. So as you can see, multiplying by a negative constant, or maybe even just a negative, will actually flip the direction. And since in this case it's just 1, it won't cause it to grow larger or smaller because multiplying anything by 1 will keep the size the same. Now, if we multiplied the vector by, let's just say negative c, and let's just say c is greater than 1, then it will get scaled up. Well, first off, it'll get flipped because of the negative, so we see that it's flipped here. But not only that, but it'll get scaled up by a factor c. So maybe the new vector might be a little bit larger than before. And that's how scaling works. Now let's talk about adding and subtracting vectors. And we are just about to talk about dot products. So just wait just a little bit more. So as you can see, you can add or subtract vectors. Now, it's kind of intuitive, but when you add two vectors, you're adding the x components or the changes in x's together to get the total change in x, and you're adding all the delta y's or the changes in y together to get the total change in y. So pretty intuitive there, and we can see that in this image where, let's just say, the delta x here is positive and the second delta x here is positive. So you have an overall delta x that's the combination of these two as shown here. Now for the delta y, it's a little bit more interesting. We have a positive delta y or a positive y component for this first vector u. But for v, we're actually going to move back down to where we started in terms of the y component. And this will be, well, we're going down, so it's a negative delta y. And in the end, we have no change in y. So notice how we're just combining these two components together to create the overall change in y, which in this case is 0. So in the end, you have a horizontal line, and this is actually the sum of the two vectors that we added together. So the vector u plus v is the sum of these two. And when adding vectors, pictorially, you want to draw it starting with the point and ending at the point, and then you're going to start off the second vector at the ending of the first vector and just continue on until you end there. Now, what about subtracting vectors? Same idea. You're going to take the differences between the changes in x and the differences between the changes in y, and in this case for the picture, it's a bit more complicated, but we could figure this out. So we have a vector u and v, and we want to find the representation of the vector u minus v. Now, how do you do that? Well, we can think of u minus v as u plus negative v, since they mean the same thing. And we know what negative v looks like. It's just this vector, but just flipped around in a 180. And since the scale factor is basically 1, the size won't change. And in this case, we're simply adding two vectors again. And as we saw before, adding two vectors, you're simply going to connect the dots and trace a line from point 1 to point 3. So in this case, point 1 to point 3 looks like that. And that's the vector u minus v, or u plus negative v. Now that we're done reviewing this, let's talk about dot products. Now let's talk about dot products. A dot product is simply an operation done on vectors, and we'll explain why soon because it has a lot of practical applications. But first, we need to know what it is. Let's say that the vector u is simply u1 comma u2, where u1 is the x component and u2 is the y component. And let's say the vector v is v1, v2. Now, when we take the dot product, and we don't call it multiplication, although it might seem like multiplication, it's actually a dot product. And that's the formal name for it when you're dealing with vectors. So the dot product of these two vectors, which are the same thing as these two vectors, what you will do is that you will multiply the x components and you'll add it to the product of the y components. So u1, v1 plus u2, v2. And that's what a dot product is. Pretty simple, right? Now you can also do this for 3 dimensions as well. Same idea where you're simply just multiplying each of the components and taking the sum of them. And you end up getting u1, v1 plus u2, v2, plus u3 v3. Voila! Now before we do the practice question, let's go over some rules. Now you don't necessarily need these rules, but you'll find these helpful. So the dot product of u and v are the same as the dot product of v and u. Notice how we switched the order and it doesn't even matter. It just looks like multiplication. 3 times 5 is equal to 5 times 3. Now the second rule is the distributive property essentially for vectors when doing dot products. So the dot product of u and the sum of v and w is simply the dot product of u and v plus the dot product of u and w. So notice how this is like the distributive property where 3 times 5 plus 2 is equal to 15 plus 6. And notice how I just distributed it and added them together. And you get 21, which is the same as doing this. And look at that. It's the same exact answer. Rule number 3 is kind of a property that might be a little bit tricky at first, but you'll get it soon. So we're not going to distribute it. We're instead just going to cling it on to one of them. So when we multiply a constant by a dot product, we're simply going to cling on the constant onto, well, one of the two vectors. So you can either cling on the c to this vector or this vector. And the same idea goes kind of for multiplication. 2 times 3 times 2. Well, you could go, let's say, 2 times 3 times 2, or you could do 3 times 2 times 2. So notice how I made the 2 cling on to different numbers, but they all are equal. So let's look at rule number 4. The 0 vector, and the 0 vector is simply 0, 0, or 0, 0, 0 if you're dealing with 3D vectors. And if you multiply the 0 vector by basically any vector, you'll get 0. And this might be pretty obvious, but let's prove it. So the 0 vector dot product with a random vector v1, v2 will yield this and this. And notice how 0 times anything is 0, and 0 times anything is 0, and you get 0. So that's kind of a proof on why dot producting the 0 vector and any vector will yield 0. Now, our final rule will involve some new concepts, but we'll figure this out. So, the dot product of, well, a vector and itself will yield the norm of the vector squared. Now, what is a norm? Well, the norm is simply the magnitude. Now, the magnitude, we can kind of prove this by looking at this triangle. So this is the vector v, and it has the x component and y component. And if we know from geometry, from the Pythagorean theorem, we kind of know that a squared plus b squared equals c squared. So v1 squared plus v2 squared equals, let's just call this magnitude, or r, the magnitude of the vector. So this distance over here will be r. Now, if we solve for r, we get the square root of v1 squared plus v2 squared is r, and this is the norm of the vector, or the distance of the vector. So r and the norm of the vector v mean essentially the same thing, but we tend to stick to that one because we're dealing with vectors. So we can call this the norm, the magnitude, or the size. All of these two are more common. Now let's go back to the question. So in this case, we can actually prove that the dot product of a vector and itself will yield the norm of the vector squared. So we know that the vector v can be represented by v1, v2, and we know that the norm of that vector is basically the square root of v1 squared plus v2 squared. And if we square the norm, you notice how you're just removing the square root sign since they're inverse operations, I guess you could say, and you get v1 squared plus v2 squared. Now notice how this is equal to the dot product of a vector and itself, since you're simply doing v1 times v1, or v1 squared, plus v2 times v2, or v2 squared. So we just proved that the dot product of a vector and itself is equal to the norm squared. Now let's not dwell too much on rules and actually do some practice, because that's the best way to learn about these things. So in this case, we have 3 times this vector dot producted with this vector. I don't know if dot producted is a word because I'm pronouncing it kind of weirdly, but basically the dot product of these two vectors times a constant 3. So we can do this in many ways, and I would like to use one of the rules. And one of the rules stated that we could actually distribute that constant to one of the vectors. So we could cling it onto, let's just say, the first vector. So let's cling on this constant to the first vector. So let's do that. So let's cling this constant on, and we know that 3 times 2 is 6, 3 times 1 is 3, and 3 times 0 is 0. Now, we have to actually dot product this with the second vector, 2, 1, 0, and we get 6 times 2, 12, plus 3 times 1, 3, plus 0 times 0, 0, and this is 15. Now let's deal with this with a method that is more intuitive, I guess, that doesn't use any of the rules. So let's dot product these two first, and notice how they're the exact same. So that's pretty interesting. We could use the rule that the dot product of these two will simply be the norm of this vector squared, but we're not going to deal with that. We're going to do this the old-fashioned way, just in case you don't know the rules. So this would result in 2 times 2, 4, plus 1 times 1, 1. And notice how after you deal with that, you're going to multiply by a constant 3. And 3 times 4 plus 1, well, 3 times 5 is 15. Look at that, the same answer using 2 different methods. And there are probably more methods, but we won't get into that because we understand how everything works, and that's all I need you guys to do. Now, the most important application, in my opinion, of dot products are that you can actually find the angle between two vectors with dot products. Now, I'm not going to prove it here, so memorize this. The dot product of two vectors is equal to the norm of the first vector times the norm of the second vector times cosine theta. Now, what is theta? Well, theta is simply the angle between two vectors, in this case between u and v. And it will always be positive because an angle in this case will be positive. So keep a note of that, and let's do a practice problem using the formula, of course. Now, before we use the formula, let's actually just draw this out. So the vector 0, 0, 1, well, the x and y will be 0, but it'll have a z component of 1. So using a different color, let's just use maybe yellow. So the first vector will kind of look like this. Now the second vector is 2, 1, 0. So the x will be 2 and the y will be 1. And you won't be moving up and down because the z component is 0. So our second vector will be like that. And just to keep a note, I'm starting at the origin for simplicity, but you could technically start anywhere in the 3D space, but starting at the origin is the smartest choice in this case. So in this case, we can actually think about this, and we can kind of see that this is a 90-degree angle, and this is because it simply looks like this. It's kind of laid back on the corner of a wall if you think about it. Think about this as a floor, and think of this as a corner of a wall. If you kind of look at it from a different perspective, you can see that it is going to be a 90-degree angle. But we're not going to look at this for proof. We're going to actually do the math to prove it to ourselves. So let's do the math. What you'll do is that you're going to take 2, 1, 0, dot product with 0, 0, 1, and this is equal to the norm of the first vector. Now let's do some mental math here. How do we find the norm? It's the square root of this squared plus this squared plus this squared. So the square root of 2 squared is 4, plus the square root, 2 squared plus 1 squared is 5, because 4 plus 1 is 5, and of course 0 squared is 0. So you're going to put that all under the radical, and we're going to find the norm of the second vector. And in this case, we're going to put all the squares under a square root. So 0 squared is 0, 0 squared is 0, and 1 squared is 1. So 0 plus 1 is 1. And this is multiplied by cosine theta. So now let's actually solve for the dot product. 2 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0. Wow. Now this is equal to rad 5 cosine theta, and we can divide both sides by rad 5, and notice how the 0 will still be 0. 0 equals cosine theta, and we take the inverse cosine of 0 to get theta, and we can think of this as what angle will have a cosine of 0? Well, if you know, the angle is going to be pi over 2, or 90 degrees. And this is basically because at 90 degrees, the point is, well, 0, 1. And cosine is always thought of as x over r. So 0 over r, which is always 1, is always 0. Now, if you have your own method of finding inverse cosines, just do whatever is comfortable for you. But in that case, I like drawing out pictures, and doing that allows me to find my angles. So in this case, we just proved that theta is pi over 2. So the angle between these two vectors is pi over 2, or 90 degrees, just like what I predicted based on drawing it. So pretty cool, right? Now, there's actually a neat little trick. When the dot product of two vectors is 0, the angle between them instantly becomes 90 degrees, or pi over 2 radians. So here's to prove. Well, we kind of just proved it, but let's prove it again. So we're assuming that this is 0, and if this is 0, then of course we don't care about the norms, because if you divide 0 by the norms, you're still going to get 0. And you end up getting 0 equals cosine theta, and solving for theta, you get 90 degrees, or pi over 2. So this is a very important rule that will be applied, and you should memorize that. Now let's move on to talking about other applications of dot products. And the first application we're going to look at is actually, well, physics. So, before we learn about physics, let's actually talk about a new concept that we can learn using the knowledge that we just learned. So we have something called projections. Now let's actually move this down a little bit. So a projection is essentially a shadow. So in this case, W1 is the shadow of, the vector u cast upon the vector v. So you can think of the vector v as kind of like a platform for which this vector can cast a shadow upon. And in this case, the shadow is W1. And in this case, W2 will simply be that final vector that kind of connects the vector forming the shadow and, the shadow itself. So we don't really focus on this vector. We care more about this shadow vector, as I'd like to call it. And as you can see in this image, we notice that the vector W1 plus the vector W2 will give you the vector U. And that's something cool that you could use just in case you need to solve W2. Now, before we continue, let's actually have proper notation for this. So W1, which I dubbed the shadow, is equal to the projection of the vector u over the vector v. So that basically means the projection, or kind of like the shadow of u, projected onto the floor created by vector v. So that's a nice way to think about it. And let's actually look at the notes that I wrote. So let's look at this. Note, the size of the vector v, or the platform or the ground that the shadow is being cast upon, doesn't matter, since the vector v only gives the direction for the shadow. The size of u, so that's the u, the thing creating the shadow, is what determines the size of the shadow, which we call w1. Now, let's actually look at some other notes. So, as we can see, this vector v, as I just said about twice, gives the direction for which the projection will, form. So if you notice, the um, the vector that gives basically the platform for which the vector u will cast a shadow upon will lie on the same line as the projection. So that's something that you should notice. And we actually have a formula. Now, we're not going to prove this, but we're going to memorize this, and it's pretty easy to memorize. The projection of u over the vector v will be equal to the dot product of u and v over the dot product of v and v times the vector v. Now, if you notice, the dot product will create a constant, and down here, it will also create a constant. So in the end, this entire thing will condense into a constant. And when we talk about constants, I call them scalars because they only have a magnitude or size, but not a direction. So in this case, we can actually condense this even more, although I like the first one because you can think of it as one u dominated by four v's. But we could simplify the dot product of v in itself to become the norm of the vector v squared. Now I highly prefer the first vector, or I mean the first formula, because it's easier to memorize. And yeah, so let me undo this, and there's a formula that you should have memorized. And it will be very important, especially when it comes to doing problems like this. So this problem involves us finding the projection of 3, negative 5, 2 over the vector 7, 1, negative 2. Now, in order to make sure that I do this correctly, I'm going to look at an answer key, and okay, now that I have the answer, let's actually do the projection and do it correctly. So, in this case, we're going to project this over this. So we're going to take the dot product of u and v, and I'm going to skip a lot of steps. So let's just multiply 7 times 3, and let me do this in a white. So 21. 1 times negative 5 is, well, negative 5. Negative 2 times 2 is negative 4. And we're going to divide this by the dot product of the vector v and itself. So we know that 7 times 7 is 49. 1 times 1 is 1. Negative 2 times negative 2 is 4. And we're going to multiply this entire constant or scalar by the vector v. And we know that v is 7, 1, negative 2. So let's make that pointed because we want to connote that as a vector. So 21 minus 5 minus 4 is, well, 16 minus 4, or 12, over 49 plus 1 plus 4, well, 54. And we can simplify this and say that it is going to be 6 over 27. And hey, look at that. It actually simplifies. And we're going to actually divide this even further. So 6 divided by 3 is 2. And 27 divided by 3 is 9. 2 over 9. And let's just rewrite this as 2 over 9 times the vector 7, 1, negative 2. And we can simplify this even further by distributing this constant to each of the components. And we end up getting, well, 14 over 9, comma, 2 over 9, comma, negative 4 over 9. And that is our answer. And that is correct according to my answer key. So now let's apply this to physics. Now why physics? Well, we basically create math for physics and other sciences, but physics is a math-demanding science. So let's respect that and let's do this problem using projections. Now, something that we should learn is that the force due to gravity in the direction of motion is the projection of, well, the force of gravity over, well, the direction of motion indicated by the vector v. So the best way to learn about this is actually to do a problem rather than to arbitrarily describe this. So in this case, we have a 500-pound cart rolling up a hill. So the direction v is, the direction that it's rolling, the direction of motion. Now, when we do gravity, something cool about gravity is that it always points down. So we're going to point gravity straight down. And the weight of the cart is equal to, well, the force due to gravity. The weight is the force due to gravity. That's the literal definition of weight. So in this case, the force due to gravity, which we can connote as, well, the vector of the force of gravity. So the norm of that would be the magnitude, and that would be the weight. So the weight is 500 pounds, and we know that gravity points straight down, and when things point straight down, you know that there's no x component because it's not changing in the x direction. It's changing in the y direction, and it's going down. So it's going to be a negative change in the y direction. And in this case, the change will be negative 500. And notice how the norm of this vector will give you 500. So that's something cool. And this is equal to the vector of the force of gravity. So we have a vector for the force of gravity. What about the vector for the direction of motion? Well, we actually have an angle, and the angle is 30 degrees. Now, how do we find the vector for that? Well, do we care about size? Well, no, we don't. Because at the beginning, we talked about how the size of, the platform, which is described by the vector v, doesn't matter because it simply gives direction for which our vector u is going to cast its shadow upon. So we don't really care about the size of this vector v. We just want to find a vector that best represents it. So in this case, I want to find something called a unit vector. A unit vector is any vector with a norm or magnitude of 1. So in this case, you can think of this as 1, and we know that the angle is 30 degrees. So how do we find the x and y component? Well, this is a 30, 60, 90 triangle, and from geometry class, you should know that the side that is opposite of 30 degrees will be half of the hypotenuse. So half of 1 is 1/2. Now the other side is going to be this times rad 3. So 1/2 times rad 3 is rad 3 over 2. And look at that. We have the components for our vector v. Rad 3 over 2, comma, 1 over 2. And incidentally, this is actually equal to the vector cosine 30 degrees and sine 30 degrees. And this leads to a cool conclusion that if we have an angle, we can essentially find the unit vector, and the unit vector for that vector in that angle will be just cosine theta, sine theta. So that's definitely something you should memorize because that's also important and fundamental as well. So now let's actually solve for the force due to gravity in the direction of motion. And that's equal to this projection. Now, from this point on, it's simply math. So the projection of the vector v, which we know is rad 3 over 2, comma, 1 over 2, and we're going to have that as the thing casting the projection. So this is 0, negative 500 is equal to, now I'm going to do some fast math, and we know that the top is going to be this dot producted with that. So rad 3 over 2 times 0 is 0. 1/2 times negative 500 is negative 250 over the denominator, which is basically the dot product of this vector and itself. So rad 3 over 2 times rad 3 over 2 is actually 3 over 4. And 1/2 times 1/2 is 1/4. And 3/4 plus 1/4 is 1. Now we simply have to multiply that by the vector down there. And look at that, we basically have an answer right here. So in the end, our vector for this projection is going to be, well, negative 250 rad 3 over 2, comma, negative 250 over 2. Now what does that even mean? Well, we remember that we have a cart, right? And it's moving in that direction, and there's a vector due to gravity, and we want to find the vector representing the gravity acting in the direction of motion. So in this case, this vector is actually going to kind of look like that. And this would just basically be all this right there. And this is basically the force due to gravity in the direction of motion. And, well, it's not in the direction of motion, it's acting against motion because, this cart wants to go up, but it's sliding back down. But it's along the same line, which is what I mean when I say the same direction, or I guess I could say the same line of motion. So in this case, the line of motion is the same, and this vector over here is the force due to gravity in this direction rather than in this direction. Since we don't really care about that direction, we care about how much force due to gravity is pulling this cart down. So apparently, we haven't really solved this problem yet because we actually have to find the magnitude of this vector in order to find the actual force due to gravity in the direction or in the line of motion. So to find the norm of this, or the magnitude of the force, we simply do some math. So in this case, we take the square root of, well, this squared. Now what is that squared? Well, I kind of want to simplify this. So this would be negative 125 rad 3, and this would be negative 125. So let's just make this our new vector, and let's simplify from there. So we're going to have negative 125 rad 3 squared plus negative 125 squared. And this will give us the magnitude of that force due to gravity in the line of motion. And using a calculator, we get a pretty cool answer. So negative 125 squared, well actually let's do negative 125 times rad 3 squared plus negative 125 squared. And we end up getting the square root of 6 to 500. And guess what? The square root of that is going to be 250. And what are the units for force in this case? Well, we're given the weight in 500 pounds, which is the force due to gravity. So our answer should be in pounds. And that is the answer. So in this case, for this cart over here, although it weighs 500 pounds, the force pulling it back down due to gravity is going to be 250 pounds. So ideally, this force that's pulling this cart back up should be greater than 250 pounds if this cart wants to move up, or else it's going to start sliding back down. So the last topic in physics that we have to discuss before going to our ultimate question about that bond angle that we want to know is work. Now, work is, well, force times distance. That's the simplest definition. But when direction is involved, it gets a little bit more complicated. So work is done by constant force in this example, acting in any direction. So this force will act in any direction. So let's just say that this object is moving in the direction of the vector v. Now, it's moving that way, but the force is being pulled in a completely different direction. Now, what ends up happening is that the only force that we truly care about is the x component of the force. So we can call this, well, the x component of the force in the form of a vector, and it's going to move horizontally. And guess what? The force in the x direction times the distance traveled by this block will actually give us the true work. And if you're wondering what happened to the other force, well, guess what? Only this force matters. It's the force in the same direction in the direction of motion that matters. So we're going to focus on that. And guess what? That really strikes a bell when it comes to projections. Because guess what? The force in the direction of motion, or in this case, the force in the x direction, will be the projection of the force vector upon, well, the direction of motion indicated by v. So as you notice, the shadow created by this force will actually give us the force in the x direction, in the form of a vector, of course, in the same direction as the vector v, which is the direction of motion. Now let's do an example problem, because that's the best way to learn, to be honest. So in this case, we are going to have to find work. And before we do the question, let's actually find the formula for work, because we only found the formula for, well, the force in the direction of motion. So work is actually the force in the direction of motion times distance. And why isn't there a vector up here? Well, it's essentially because this is actually a magnitude. They're both magnitudes, but we have vectors in this problem. So how do we fix that? Well, guess what? The magnitude of the force in a direction of motion is simply the norm of the vector of motion for the force. And that is because the norm will give us the magnitude. So we take the norm of the vector representing the force in the direction of motion, we'll get the magnitude of the force in the direction of motion. And we multiply that by the distance traveled. And ideally, this distance is going to be linear so that we don't have any complications. And our force is going to be constant as well. And by doing all this, we won't have to use calculus. And that's great because we're not ready for that yet, in this chapter at least. We will be ready for that in future chapters. But for now, let's focus on constants. So constant force and a linear distance. And guess what? This vector, which is the vector of the force and direction of motion, is equal to this as we just discussed. So substitute that in there, and guess what? We have a formula for work in terms of projections. And you can even go as far as to say that the work done is equal to the norm of the original force vector, so the force vector in the whatever direction that wants to go, times cosine theta. And what ends up happening, so how does this work? Well, to put simply, if we take the norm of our original force vector and we multiply by cosine theta, what ends up happening is that we will get the norm of only the x component of the force. And that's what we intended to do in the first place when we were doing projections. So same idea here, and of course you're going to multiply by the distance d, since in essence work is force times distance, and assuming that these two are in the same direction. Let's do an example problem, because we all need that sometimes. So in this problem, we're going to use this formula right here. Now, before we do that, we have to figure out what that force vector is. Now, we know that the norm of the force vector is going to be 50 pounds, since that's what the problem says. And it's at a 15-degree angle. Now, here's a neat little trick that you might have learned before, but I'm going to show you how to do that now. So to find the vector f, you can simply multiply, well, the norm of that vector times the unit vector representing that direction. So in this case, the unit vector representing that direction is cosine 15 degrees, sine 15 degrees. And when you do that, you will get, well, essentially the vector of the entire thing. So in this case, I'm going to not simplify, and we know that this is 50. So we get 50 cosine 15 degrees, 50 sine 15 degrees, and that is actually the vector representing f. Now, we also have another vector, which is the vector v. And remember, we don't care about the size of this. And in this problem, we can see that it's obviously going horizontal. So let's just say this is 1, 0. And now that we have that, we can actually do some math. So let's do some work, no pun intended. So let's write out the projection formula. So projection of 1, 0, and the force vector is going to be 50 cosine 15 degrees, 50 sine 15 degrees, and this will be equal to, well, let's multiply this out. So this times 1, well, that's going to be 50 cosine 15 degrees over the vector dot producted with itself. So it's going to be 1 times 1 is 1, plus 0 times 0 is 0. And we're going to multiply by, well, that. And you end up getting a vector that looks like this, 50 cosine 15 degrees, comma 0. So that is the projection. And why do we find the projection? Well, remember, this projection is equal to the force vector in the direction of motion. Now all we have to do left is multiply this by the distance traveled, and voila, we have the work done. So work is equal to the norm of this projection as we just solved for. So we're going to take the norm of that vector or the projection that we just solved for. And the norm of this is simply just, well, I'm going to skip a step and tell you that the norm is going to be 50 cosine 15 degrees. And this is because if you take the norm of this vector, you get the square root of essentially 50 cosine 15 degrees squared. And guess what? The square root and squares cancel out, and you're left with the x component. And we're going to multiply by the distance traveled. In this image, the box traveled from 0 feet to 100 feet, and that's actually 100 feet. Now we have to be careful about units. So this force, this magnitude, as we described at the beginning, where work is the magnitude of the force in the direction of motion times the distance, this force is actually in pounds because we solved it in terms of pounds since the problem gave us it in pounds. So we have to actually write pounds. And in the end, work is actually equal to, well, basically this times this. Now we can actually use a calculator to solve for this. So we get 5,000 cosine 15 degrees, and the units for work in this case, it's going to be foot-pounds. Now we can type this into a calculator, so make sure that your calculator is in degrees, and 5,000 cosine 15 is going to be, work is equal to 4829.6 foot-pounds. And that's actually our final answer. So now that we learned about how we can use dot products to find both force in the direction of motion and work in the direction of motion, let's now solve one last mystery. So upon learning all this stuff, let's now unveil the true question at hand that we wanted to solve right at the very beginning. And it's kind of an application of dot products in chemistry. Look at that, right? Anything can be applied to anything, and at the end, you get something truly incredible. And in this case, we're going to prove, as I said at the beginning, why the bond angle in a tetrahedral molecule is 109.5 degrees. Now, we can find bond angles quite easily for most of them. For example, trigonal planar is simply 120 degrees because a circle is, as we know, 360 degrees. And we're simply splitting it into 3 equal pieces. So 360 over 3 is 120 degrees. Now, it's a little bit more complicated for the tetrahedral. It's 3D, first of all, and there's not really any intuitive idea for why this angle right here is 109.5. Like, that's such a random number. Well, now I'm here to prove to you, using everything we learned in the last 50 minutes, why the bond angle is 109.5 degrees. So, to start off, we have to know what a tetrahedron is, which is what the word tetrahedral is based off of. Tetrahedron. Now, tetrahedron is basically a triangular pyramid, but guess what? All the sides are going to be triangles. They're going to be equilateral triangles, and they're all going to be equal, as shown in that picture. So you can kind of see it, but we have one side, two side, three side, and in the back, which you can't really see, four sides. So the shape, this tetrahedron will have four sides, and right smack in the middle will be the center, or in this case, the center will be the center atom. And our goal is to connect the center atom to two other atoms and find the angle between them. So to do that, we need to model the tetrahedron in the 3D space. Now, what's cool is that a tetrahedron can actually be inscribed in a cube. So in this case, I drew a cube, and I drew a tetrahedron by connecting this point, this point, this point, and this point. Notice how all four of those points are actually corners of the cube. And by connecting these 4 points in this particular way, we get a tetrahedron. It's kind of hard to see, but you can kind of see one side over here, one side over here, one side over here, and of course, one side, well, it's kind of hard to tell, but basically there's one side in the front, two sides in the back, and one side at the bottom. So let's get rid of these distracting arrows, and let's think about this. So what I did was that I inscribed a coordinate system right in the middle of this cube, and I will label the ends of, I guess, the endpoints of this side as 1 to make it simple. So in this case, from the center to this side, it'll be 1. From the center to this side, it'll be 1. And from the center to the top side, it'll be 1. So as you can see, all 3 sides are equidistant from the center, and that's what a cube is. Now, we can look at the corners, and we would notice that the corner would have a coordinate of -1, 1, 1. And this is because the corner is kind of like, you can think of it as, well, this, and kind of like, that's like, I guess you could call this halfway, or the midpoint of the side. And to get to that other point, we're simply going to shift it that way. And guess what? This distance right here is actually 1. So in the end, you have an x component of, well, actually, in this case, it's going -1 since we're moving backwards. So this point in the back will be -1, 1, 1, because, well, the x component, as you can see, is -1, the y is 1, and the z is 1. So kind of hard to visualize, but you probably should take my word for it if you can't visualize it. Now in this case, this corner down here, and note that I said down here, and that means that the z component is actually going to be negative. So since it's down there, the z component is -1, and notice that the x and y component are both +1. So take some visualization, but eventually you'll get it. And in the smack middle, we call it 0, 0, 0. We have 2 vectors now. What can we do? We can find the angle between them. So let's call this first vector over here -1, 1, 1, because we're going to take this minus this to get the vector. And let's call that u, and let's call v actually this. So 1, 1, -1. And you get that by doing 1 minus 0 1 minus 0, and negative 1 minus 0 for the change in x, y, and z. So we have these two vectors now. Pretty cool, right? Now we have to find the angle between them. So how do we find the angle between them? Well, we simply do some math, and this is the angle formula we learned. So negative 1, 1, 1. Dot product with 1, 1, negative 1 is equal to the norm. So the norm of this is 1 squared plus 1 squared plus 1 squared, or 3, times 1 squared plus 1 squared times negative 1 squared, which is still 3. And this is cosine theta. So let's actually find the dot product, and we know that it's just negative 1 plus 1 minus 1. And we get negative 1. And what is rad 3 times rad 3? That's 3. So negative 1 equals 3 cosine theta. Negative 1 over 3 equals cosine theta. And in the end, we have to take the inverse cosine of this. So we essentially have to do this. Inverse cosine of, well, negative 1 over 3 is equal to cosine theta. And we're going to use our calculator since we can't solve this by hand. Inverse cosine of negative 1 over 3 is going to be 109.47 degrees, or 109.5 degrees. So look at that. We basically just proved that the angle between these two vectors, which represent bonds, by the way, where this is the central atom, these two are the side atoms, we just proved that the angle between them is 109.5 degrees. So that's how we apply dot products to chemistry, and that's pretty cool. So that's all for this video. Thanks for watching, and have a wonderful day.